Hello, so today we are doing a test wrapper for midterm 2. So I will be discussing question 1, part B. So this question dealt with, I'll just go ahead and read the question. So it says, the configuration of 4 bodies moving in a circle is very unstable. A short time later, one of these bodies is observed to move at constant speed along the path shown in the diagram below. On the diagram, draw a vector representing the net force on the object when it is at location A and location B. So we can see the two locations here, A and B. So basically, we have a constant velocity, and we have this object that's moving. So basically what I did is I used the momentum principle and I broke the, I'll just go and explain. So I had the right idea with the algebra by breaking up dp dt into its perpendicular and parallel components. So the parallel component is 0 because the object is not speeding up or slowing down, which it tells us in the question. Therefore, only the perpendicular component of the change in momentum is affected by the net force. So, this perpendicular component is the component that causes the object to change direction. So we're only concerned with the thing that's causing the ball to change direction. So that's all we want to draw. We just want to draw that force that makes it change direction. So what I had done is I just drew the net force in the direction of the change in motion. And, well, this is not right. The problem is that the object is still moving with some velocity. So as it's going around this path, it's constantly keeping that its speed. So I guess I should change this to speed. But it's constantly keeping that speed, and so it's kind of similar to kicking a bowling ball. Let's say you have a bowling ball that's rolling along in the positive x direction. Now let's say I kick it in the y direction. It's not immediately just going to go straight into the positive y direction, which is what I drew. The problem is that the ball still has some velocity in the x, so my force is not just going to immediately change its direction. It will change it, but it's going to change it along the kissing circle. That's what we call it. So if we go down here to the correct way that they've done it, so basically we determine that the perpendicular component is the change in momentum the perpendicular component of the change in momentum corresponds to the net force. So, using the idea of a kissing circle, this perpendicular force is equal to mv squared over r. Because we have a circle, so we have, which is that kissing circle, so we have that, and then we only have the perpendicular component of the change in momentum, which is also equal to the net force, which they have written right here. F net perpendicular is equal to mv squared over r. And so we can see in this equation that r affects the force. So the greater the r, the smaller the force is going to be. So we can see in A here, we can see that r is going to be pretty small because the kissing circle is only going to be composed of this area here. So therefore the net force is going to be rather large. Whereas in B we have this whole giant kissing circle, so the radius is pretty big, so the net force is going to be relatively small. So that's why the two net forces for A and B are written that way. So I guess the main thing that you want to take from this is that although dp dt parallel is constant, it is still there. There is, like, there, I'm sorry, although dp dt parallel is still is constant, or I'm sorry, is zero. It's constantly zero. Although that is true, um, there still is some speed for the ball. So we can't just say that the change in direction that it's now going, the new direction that it's now going, is where the is the same direction that the force acted, because we have an already initial speed, so we have to take that into effect as well. So the perpendicular net force is going to act perpendicular to its initial motion. It's not just going to go in the direction of the final motion compared to the initial motion. So it's called dp dt perpendicular for a reason. It's always perpendicular to the tangential speed, or tangential velocity. As we can see here, where they wrote p, and then its perpendicular component is dp dt perpendicular, which is the net force.